if things will work out and the computer will not choke on us, and I think we are going to have a really exciting class today, so let's hope. Before that, homework questions, anything? Yes, sir. Remind me, or if you have it. Yeah, so the overall goal is to, it comes in a few steps, but the overall goal is to find, I have a set of points. The question is about number 9 from the homework. And I want to fit a line through this set of points. And there are lots of ways to find what is the best line. How do we optimizing it? Statistics will usually work about take each data point, measure its distance from the line, either orthogonal to the line, or measure the distance vertically, the distance in the y coordinate. And then you're looking at all these distances, take the square of each one of them, because then it's easier to compute the derivative of this expression. Sum them all up, and then you have two parameters, a, b, of the line. That's not what we are doing in this question. In this question, we are saying each point is really, really important. We don't want that one far away point washed away, because there is a lot of points that are almost near the line. So everybody is as important as everybody else. So we are trying to minimize the distance. Eventually, we would like to find the line that minimizes the distance to each and every point. That is, I'm looking at one particular line, L. For this particular line, L, which is L of A and B, for this particular line, I'm looking at D1, D2, D3, the distance to each one of the points. It's the orthogonal distance to the line. It's not the vertical distance, the distance between the y. You're asking, how close is this line from each and every one of the points? And then out of all the parameters, A and B, expressing the line as y equal ax plus b, among all the A and B, you will find the one for which the furthest away point is as close as possible. If you're confused about this definition, let's think for a moment about the definition of a center of a point. I have a cloud of points here, and I'm looking for the center. For example, the center of the smallest enclosed disk, which is actually a problem that we'll talk more about it. But what does it mean? I take one possible candidate of the center, let's call it C. I check from C what is the distance to each one of the points. This is my data points, P1 dot 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 Pn. This is my first attempt to place a center. And then I can ask, move the center so the sum of distances will be minimized, or sum of square of distances are minimized, or the furthest away point will be as close as possible. Put the center so that it is as close as possible to each one of the points. There is no, you are saying the distance either for the line or for the point is 17, means there is no point whose distance is more than 17. And then I'll try 16, 15, 14, try to minimize. So the question is essentially to say that, back to our line, that's the criteria that I'm looking at. Find a line for which the distance to the most remote point is as close as possible. And that by itself is a decent problem. So like harder problems, so I'm breaking it into a few steps. Like suggesting a few steps along the way. And I'll sprinkle more clues as we are getting closer to the deadline. Other questions? You can think about it in a sense as a caliper question. If you think about caliper, maybe I'll put it in the caliper is this measurement tool, and you are somehow try to fit a caliper where it's as narrow as possible so that you can squeeze all the points inside. Other questions from the homework? Perfect. Zoom people, see your chat. I'm not sure what the status of the volume, so if you're speaking, I don't know what the scenario, but if you'll type, again, no question, okay. So we are done with line sweep. We were able to squeeze a line sweep in one meeting. It was nice. Remind yourself, because there will be, in homework 2, I'll ask various questions that are all based on this paradigm of the line sweep. It's also taught sometimes in algorithms course. So you'll find the online, if you don't like my accent, you'll find plenty of other accents over YouTube of either algorithms or computational geometry course, and various modification of line sweep, sometimes only to find if two segments intersect and stop if they do, sometimes to find all the intersection points, sometimes only to handle cases where segments are axis parallel, namely either parallel to the x-axis or y-axis, horizontal, vertical, and so on, many variants. Okay, and we are heading toward really, really ingenious algorithm that made when it enters the computational geometry in its way, made a very nice part about that will help us calculate good diets. So we are starting with linear programming, jumping at a few examples. So your diets from now on will not be very rich in ingredients. That is, your diet from now on will be based only on bananas and oranges. We'll decide how many of each one and nothing else. If you want more ingredients, then we will not talk about linear programming in 2D. If you want 3 ingredients, then it will be linear programming in 3D. 4 types of ingredients. I think that you got the message. So we will have some 2 parameters. X will decide how many bananas we are going to consume, while decide how many oranges we are going to consume daily. And we would like to be both budget-wise smart as well as satisfies various constraints about vitamins. That will be our definition of a healthy diet. So it's somehow narrow view of food, maybe, but that's fine. But we will play a lot in this with half spaces in higher dimensions, or in half planes in 2 dimensions. So what are half plane? So half plane is a region of the plane that is bounded by a line. All the points that are on one side of a line. Example, here is H1, which are, this is a long way to write it, all the pairs of xy, all the infinitely many points of xy, such that y is larger than x. That y is larger than x. So first, let's check, where is the line y equal? Where are all the points for which y equal? Exactly x. This bounding line, that all the points such that y exactly equal x. Not larger than, exactly the same. Everybody agrees? This is this line. Yeah. Now, if I take a point on this line and increase the y by a bit, I'm leaving the line but only moving upward. So let's define a half plane. Fair enough? So H1 is a half plane that here are all the points above this line. When I'm drawing it on the whiteboard, see, it's hard to draw a lot of points. Usually I'll draw a line. Not in white, usually I'll draw a line and then add some fur to this line to indicate what side I'm referring to the half plane. So in this example, it of course will be the line y equals x, and the fur will refer to the plane y is larger or equal than x. Now, I didn't want all my planes to go origin, so here is another half plane. All the points xy, now I drop the xy, starts to write it in a more compact way. All the points xy, such that y is smaller than minus x. The minus implies this line goes downward. X increase, then the y decrease. Plus 3. So if it was without the plus 3, it would be this line, 45 degrees. The plus 3, just move it a bit upward. And the half planes of all the points y, such that y is smaller than minus x plus 3 is actually, as opposed to the image, I was wrong with the text. The text is not taken from the front. It's actually larger or equal. Y is larger or equal than minus x plus 3. Okay, please correct it. This one. And here is one such half length, all the xy such that y is larger than x. Here is all the half length such that y is smaller than minus x plus 3. We said this one plus this one were a point that satisfies all the pairs xy, such that xy are satisfying this constraint, y is larger than x, and satisfying this constraint, that y is larger than minus x plus 3. That is, I'm in the a point that satisfies both conditions has to be in the intersection of both sets. A pair xy, a point that satisfies both this condition and this condition, means it is in the intersection of the two half planes. H1 intersection H2. Okay, and we'll work a lot with such intersection. A bit promo to where we are going. A point here will be a diet, how many oranges and how many bananas I'm going to consume per day. And if I'm getting enough many units of vitamin A, then I'll be in one half plane. If I'm getting, with this point, enough many units of vitamin B, I'll be in the other half plane. And if I'm getting enough many units of both vitamin A and vitamin B, I'm in the intersection of these two half planes. So you see, one half plane, another half plane, and the intersection, this infinite wedge. Dropping the third half. Where is H3? H3 are all the points xy such that I don't care one bit what is x, but y is smaller than 3. Where is a line y equals 3, no matter what is x? This is a horizontal line. Going through, where does it cross the y-axis? That 3. Exactly here. And the half planes are all the points just below it. Of course, switching the sign would mean all the points above it. But the line would stay the same. The boundary is the same. Now I can speak about the intersection of H1 intersected H2 intersected H3. What is this intersection? This triangle over here. Yeah.
So for the top right one, isn't this supposed to be y greater
Yes, yes, yes. What I said. It's a typo, but because I made it with GeoGebra and took a picture, I will not correct it in real time. But yeah, the sign here is wrong. I mean, the line that bounding it is fine, but this half plane that describes here is everything below this line. OK. Is intersections of convex sets convex? If I have two sets, A and B, and I'm looking at A intersection B, is this convex or not? You might have it in the homework, actually, but it doesn't matter. We'll spoil it for you. Convex or not convex? Intersection of two convex sets. It is convex. And the proof? It's easy. What's the definition of convex? If I'll pick one point of B and another point of B, and I look at some arbitrary point on the segment connecting them, this point must be in B as well. That's the definition of convex. Now, pick one point in the intersection, another point on the intersection, look at the segment between them and pick some points on this segment. Because B is convex, this point must be in B. Because A is convex, this point must be in A. Remember A and B? No, these 2 points that I picked are both in A and in B. That's what I need to put. So the middle point here in between belongs both to A and to B. So it also in the intersection. So the intersection of A and B is convex. Why is this relevant for us? Half plane, a half plane is convex shape. Another half plane is another convex shape. Their intersection is convex shape as well. By the way, in this case, the intersection is bounded. In this case, it is not. It goes all the way to infinity. That's fine. OK. We don't have to go through the vector algebra notation, but I thought that it's no harm if I'll remind you or tell you for the first time what are the very basic algebra first class 101 school level, and because it will make some notation later maybe easier. But you can get away, if you don't like these notations, it's fine. You can get away the whole chapter of linear programming without mentioning vectors. But if you feel comfortable with vectors after this talk, that's fine. And I will define everything that I use. So let's talk for 5-10 minutes about vectors and what can we do with vectors. So a vector V in the d-dimensional space is just an order list of d numbers. That's one way to think about them. V1, V2, V3, all the way up to Vd. One way to define vector in a way that nobody understood what I mean, but formally it is fine. If I think about two vectors now in the Euclidean plane, I can think about one vector, V. And in this slide, I was pretty much consistent. Wanted to highlight that something is a vector. Some books will say I'll put the vector sign above it. Some books will say I'll write it in boldface. In this slide, and I left it later, I did both just to highlight what is vector and what is just a single number. Single number is a scalar. Scalar, just a single number, vector, a list of several numbers, which has very nice geometrical meaning. If I'll think about the vector 2, 3, I can imagine the point 2, 3. And this is a very ad hoc version, and people sometimes disagree about it. But I can identify, for the time being, this vector v with a point 2, and doesn't make sense, to 1, to 1, to 1, and this will be the one vector, v. So you can think about it sometimes as a point. When you think about when you decided where the origin is, then you can think about this list as the coordinates of a point. Think about an arrow that goes into this point from the origin, 0, 0. Okay. I can define another vector, u, which would be, I don't know, 1 and 2. And I can define what is u plus v, which is what? Geometrically, it means take u, take this u, the size about of a marker, put the marker here. That's where the marker got to. Right? So this is a parallelogram. So if u plus v, which would be x of u plus x of v, comma, y of u plus y of v. Okay. X of u is just, y of u is just the y coordinate of this vector. Right, you are summing up the x coordinate, you are summing up the y coordinate. That's how you are doing subtraction. 0 vector, you are adding nothing. U minus v, you are just adding minus the vector. News to anybody here? Okay, a bit more notation. U dot product v is what? Take the first parameter of u, multiply by the first parameter of v. u1 times v1 plus u2 times v2 plus, go to the last coordinate, u d, v d, multiply them. That is just sum up from I equal 1 up to the dimension that you are working. 2 dimension, it will be 2 numbers for each one, ui times vi. Right? So if I have v, which is 2, 1, and u, which was, what was it? 1, 2, then u v equals to 2 times 1 plus 1 times 2. I can sometimes speak about the length of the vector v. I'll denote it by v with 2 bars on the side. V with 2 bars on the side. How do I compute it? I'll take v dot product v, which is the x coordinate square plus the y coordinate square, and take the square root. That's just the this is just the length of this vector that got all the way to here. Right? The x coordinate square plus the y coordinate square. Based on your facial expression, I don't, you all seems less than surprised. I can interpret it as an angle, easy to understand at least in lower dimension, and especially if u dot product v is 0, and by the way, each one of them individually is non-zero, otherwise it's meaningless, but if each one is non-zero but the product is 0, it means that geometrically the angle between them is 90 degrees. They are orthogonal to each other. Okay. Other thing that was mentioning here is how do I make half planes from vectors? And that's really going back and forth if I should denote it by p or by x, but let's keep the vector v fixed. I'm not changing the vector v. but I'm checking each vector x, which is xy. So boldface x with arrow versus small x, not boldface, with Roman x and y. Why? Because that's how you'll find it in all the books, but it is confusing that x uses two purposes. So it's x vector versus x scalar. That is just the x coordinate of the x vector. So let's think about keeping the vector v fixed. Now we are getting closer to linear programming. Keeping v fixed, v is the coordinates of v is a and b. And I'm talking about v dot product x. And I'm asking where are all the points x, vector x, such that v times x equals 0. Where are all these points x such that v times x equals 0? So we think about it a moment. Here is v, which is ab, and I'm asking where are all the points for which x dot product v will be 0, and you're realizing very soon, let's put this line orthogonal to v, and these are all the points that we need to, because we said that dot product measures the angle, so if each and every point along this line is orthogonal to v. That we will use a lot. So what happened in 3 dimensions? The same thing, the coordinates of v, wrong pens. Now in 3 dimension, x is x, y, z, triple. V is a, b, c, doesn't change. And now the set of points, all the L, which are all the vector x, now in 3D, are with another line, meaning the real numbers are 3 dimensions. All the points x such that v times x equals 0. What is this? It's a half plane, which is orthogonal to v. Going through the origin, because 0, 0, 0 satisfies it. And it's all the points that are orthogonal to v. Plane that is orthogonal to v. So if this plane is a whiteboard, v is just orthogonal to the whiteboard. OK, next. I can pick some point. I can pick some point x. I can pick some value, say 17, and I'm asking, without changing the vector v, where are all the points v times x, such that v times x doesn't equal to 0, but equals to 17. Claim, where are all these points? They are on in 2 dimensions, they are on a line. This line is still parallel, is still orthogonal to v. Here is v. This line is orthogonal to v. But now it's not going through 0, 0, 0 necessarily. It will, as opposed to the example here, it doesn't go necessarily through 0, 0, 0. Instead, it's going to some other points. And actually, if I have some point in mind, I can write it as, if I'm looking for, if you'll give me the vector v and another point q, then I can just write all the points x vector such that x v equals q v. Again, you told me what is v. You want a plane that is going through q. And there are a lot of such planes, a lot of such lines in 2D. Give me such line that is orthogonal to v, but going through q. Just compute this is in this slide 17. Compute what is v times q, the point that you want your plane to go into, and now look for all the points x such that xv equals this. OK. Now, what happens, and that would be really relevant for linear programming, I picked v and I don't change it. I keep v somewhere here, this line. And now I'll draw the line, all the points x such that v dot product x equal 1. And then I change my mind. Vx, I want it to be equal to 2. What happened to, what is the relationship between this line and this line? They are both orthogonal to v. Both lines are orthogonal to v. In 3D, both planes orthogonal to v. And this is moving somehow with respect to this one. It's just a translation of this line. Keeps changing x in the same direction. Now I want it v times x to be equal 3. Another line in the same direction. OK, and that's a point to ask you a Google question that is very relevant, actually. It demonstrates a point that we'll use many times. So here is the Earth. It's a sphere. This is an equator. OK. And I'll think about the Earth as a perfect circle. I'll think about the equator as a perfect circle. And I'll put a rope snag into this sphere. OK? There is a rope wire thread that I put around the equator. Whatever the circumferences of the Earth is, that's what I paid for this rope. And its length is L. The L is the length of this rope. And now I'm taking I'm adding to this rope 6 feet. And I rearrange it now in a co-circular way. And you see there is a gap, delta here. Without using your papers, and tell me, please, whether a cat path in this gap. Again, place a rope around the Earth, arrange it co-circular, added 6 feet, stretch it a bit more, now I have some gap. Can a cat, normal house cat, can it walk in this gap that is arranged between these two ropes? Obviously not. The Earth is huge, and I added a minusculous amount. Well, let's think about it. It's striking like, obviously not. Earth is huge. The difference in the length is really tiny. You can do the whole calculation, of course, and compute it exactly. Or you can just think about what is the relationship between R and L. L, the length of this thing. It's a linear function. Circumference is 2 pi r. Linear function. Meaning that if I take x1, take x2, where x2 equal delta plus x1, like this. And I'm asking what is delta y. I'm changing delta x by a bit. Here I'm changing, maybe delta x is a radius. And I'm looking at delta y, how much the circumference changes, or I can switch it. It's still a linear function. And I'm asking, does this delta y depends on what is x1 and x2? Delta is fixed. As long as delta x is fixed because it's linear function, delta y is fixed as well, no matter where I started. What does it imply for us? The fact that I was talking about the Earth, which is very large, is completely irrelevant to the gap that I was getting right here. I might have talked about a tennis ball that I'll do the same experiment. Now do the same experiment with a tennis ball. Put the rope around the tennis ball, very little. Add 6 feet. Rearrange it again. Right. And you'll get that 6 feet divided by 2 pi is about this height, which definitely any self-respecting cat can easily use it. But we will use it and this phenomena of linear functions, not necessarily in one dimension, that if I move a bit into some direction and it improves my cost function, then if I'll keep moving in the same direction, my cost function will keep improving. You'll see in a moment how it helps us. That problem. So that problem in 2 dimensions would mean that our diet consists of only oranges, and we need to decide about how many oranges per typo already. X would be the number of oranges, and the other one will be bananas. I'll tell you in a second which is which. X is the number of bananas, and Y is the number of oranges. And that's what we are going to consume daily. That will be our diet from now on. Now, oranges and bananas cost something, and I'll try to minimize this cost that I'm going to pay. But I'm also care for my health, and there is lots of types of vitamins, N type of vitamins, that I consider. Vitamin 1, 2, 3, 4, all the way up to N. X and Y are the only unknown. This vector X here are the only unknown. That's what we have to solve in the linear programming problem. Why this is called linear programming is beyond me. I was never able to understand. The linear, you will be able to understand what makes this problem more programming than greedy, that I was historical reasons. That's how it's called. Live with it. So X and Y is the find. In general, if we have those types of food, we had Z, W about these other types of food. What are the constraints? In all cases, we'll have constraints, which, surprise, surprise, will be half plates. What are the constraints? We are giving constants. One constant is for every vitamin of type I, A of I, comma 1 is how many units of vitamin I is in a banana. And A of I, comma 2 will be the amount of vitamin I in a single orange. X is for bananas, Y is for oranges. Somebody also, the same source of information, also told me for every type of vitamin, vitamin 1, 2, 3, 4, what is BI? BI is how many units do I need per day to be healthy? How many units of vitamin I need per day, which I can get possibly only from oranges or only from bananas or from some combination of them. So what am I looking for so far? I'm looking for a pair X and Y that I'm trying to compute that, to start with, needs to satisfy a set of constraints. What are these constraints? The first constraint would be X times A1, AI A11 times X is how many units of vitamin 1 you're getting from the amount of bananas you're taking. You're taking 3 bananas, and AI1 is 1, meaning you are getting 3 units of vitamin 1 from the bananas. Add to it the amount of vitamin I that you're getting from the oranges, how many oranges you're taking per day, that's Y, times in each orange, how many units of the same vitamin do you have? You sum them up. You know, there are no boxes in your belly. You sum them up. That to have a healthy diet, you need at least these many units of vitamin 1. This is the first constraint. The second constraint, just replace the 1 by the I by 2. That refers to vitamin 2. Vitamin 3, vitamin 4, all the way up to vitamin N. OK? And so far, there is no problem. Just add, the more you'll eat, the more you'll satisfy all these constraints. Now comes the cost issue into it. We have to buy them. There are 2 more constants given to me as part of the LP problem, 2 more constants that helps me understand how to budget by units, how many bananas and oranges I'm going to buy per day. These constants are C1. C1 is the cost of a banana. And if I'm planning to eat 5 bananas per day, then I need to buy 5 bananas, and I'll pay for bananas X times C1. Add to it, similarly, the cost of a single orange times how many oranges are you buying per day, sum them up. That's how much we are going to pay for it. And we are going to look for a diet that will satisfy all these constraints and will be as cheap as possible. OK. So I have for you, don't know if it's readable, you have the slides over here, since it will not be in the OBS, but let's keep it will not be on the video, but let's keep this slide on the side so we don't have to show it up. OK. So let's forget about the vitamins constraints. We don't need it because we have it on the other side. Let's forget about all the vitamin constraints and think about our daily budget. Here's my daily budget line. So first, how do I make it into geometric problem? Why is this relevant for linear, for geometric, for computational geometry? I'm going to make it into geometric problem because every point in the plane, x, y, I'll think about x, y as a possible diet. Quantities of bananas and oranges that I'm going to consume per day. Remember, no other sources of food. So this is xy. I'm also given the cost of a single banana and the cost of a single orange, and what is my daily budget. Once I have these 3 numbers, don't worry about vitamins for a moment, just talking money. So having these 3 numbers, I can ask, what is a line for which x times the banana cost plus y times the orange cost equals to the budget. Being on this line exactly meaning that a point x, let's move x over there, if I move x to this point will mean I think about a diet for which X times the banana cost, how much I'm paying for bananas, plus Y times the orange cost, how much I'm paying per oranges, is exactly equal to my daily budget. That's being on the line exactly. That's assuming that for a moment that I decided about the budget. Later we'll see how I optimize the budget. But right now I'll assume my budget is $159 per day. And this, every point along it is a candidate budget. This is the line. Every point below this line represents a diet that is cheaper. Surprise, surprise. Every point above this line is over budget for me. What will happen to this line, just to see that you are alive, what will happen to this line if I'll increase the cost of bananas? Increase the cost of bananas. Banana, remember, the x coordinate is how many bananas per day. If I increase the cost of the bananas, it means that per day I'll be allowed, a point here refers to a diet that consists only of bananas. If I increase the cost of a banana, I'll be able to afford less bananas per day. And increasing the cost of a banana, now banana costs $2 almost. Now banana costs $2, and of course I can afford much fewer bananas per day. Similarly, per oranges, increasing the cost of an orange, meaning you can afford fewer oranges per day. And so on for any combination of these points. Are we good with the budget? Everybody understand? This shaded region are all the possible diets that you're paying less than your max budget. Of course, later on, I'll play with it by moving the budget. Now, notice we said that, remember the three lines that are parallel? If I'm changing the budget, what happens to my line? The orthogonal direction doesn't change. Orthogonal direction to this line doesn't change. The slope of this line doesn't change. What happens to this line when I change my budget? This line keeps parallel, but its slope is the same. This angle is the same. The orthogonal vector to this line, which would be the cost vector, as we'll see, will be the same. Why am I sure that it's the same orthogonal vector? Because take 2 points on this line, look at this vector, 2 points with the same line. What is the direction of this line? It means that if I move along this line, my cost doesn't change a bit. So 2 points, this vector times the vector of the cost that you can barely see should be equal to 0, because the difference of the cost is 0. That's why I'm sure that I'm orthogonal, that this line or this plane in higher dimension is orthogonal to the cost. Good. We are good with the budget, and do remember this line is always parallel to itself, and it moves as I change the cost. It doesn't go up and down. Right? It's this cat phenomenon. I'm increasing the cost. This line keeps moving to the same direction, obviously. Good. Let's hope that we don't have any surprises from the budget. So I have some constants that you don't see about vitamin A. And playing with vitamin A, suddenly this line appeared. This line is all the points for all the diets for which you're getting exactly the amount of vitamin A that you need. Being on this line will mean you're just getting exactly the amount of units of vitamin A that you need. There is not exact meaning of what it is. When it's negative, let's not worry about it, but when this both X and Y are positive, if you pick a diet just on this line, vitamin A-wise, you're just getting the exact minimum amount. The more, the better in this scenario. The more the better, meaning that if I look at vitamin, at all the diets, all the points X, that is in the purple region, here is X, and right now I'm getting enough many vitamins A, more than the minimum quantity. Being on this half plane, I'm getting enough many vitamin A's that I need. Being on the opposite side of the half planes, I'm under unhealthy vitamin A wise. Okay, putting vitamin A aside, move to vitamin B. Vitamin B, the reason that it has different slope right here, it's also a bit washed by the projector, but here is a line that bounds vitamin B. And it has different slopes because it has different quantities of vitamin A and vitamin E, because bananas and oranges have different quantities of how many units of vitamin B they have. So remember, I have one line for vitamin A. I have one line for vitamin B. Now I can ask where are all the diets that contains enough many vitamin A. Let's wait with this. Now I'm putting both vitamin A and vitamin B. Oh, by the way, eating more than 80 oranges per day is not healthy for you, so I just chopped it in 80 just for, same for bananas, just for just for visualization purposes. But mathematically, it goes to infinity. So here are both vitamin A and vitamin B. You see a region that I don't get enough neither from vitamin A nor vitamin B. That's outside the union of the two half planes, the union. You see some region where I'm getting enough from vitamin A but not vitamin B, enough vitamin B but not vitamin A. And being in the intersection of these two regions, meaning you're getting enough, both vitamin A and vitamin B. Okay. There is also vitamin C and D. So putting both vitamin A and vitamin B and vitamin C and vitamin D, now you're getting intersection of 4 half planes. Actually, 6 if you are counting this one and this one. And another one, because I just show you the positive ones. Because you can also get it from negative dots. But being in the intersection here, let's understand again, how did I create this intersection? Essentially, took one half plane, age 1, intersected it with another half plane, age 2, another half plane, age 3, and the intersection is a polygon, more precisely, polyhedra, because it could be open to infinity, it could be bounded, the limits of no more than 80 making it bounded, but what is the boundary of the intersection? It would be this polygon. Okay, so you see this polygon with right now 4 vertices. So there's several vertices, V1, V2, which are created well. How do I define this vertex? It's the point at which there are two vitamins, I don't remember which ones, such that at this point you're getting to be on the boundary of this polygon, from one of these vitamins, you're just getting barely the minimum amount. That's to be on the boundary of this polygon. Can give it a name. The feasible region are all the points of diets that are healthy for you. Healthy from both vitamin A, B, C, D. This is the feasible region. Being on the boundary of the feasible region, meaning one of your vitamins you're just getting barely the minimum amount. You cannot go any lower than this. Being on a vertex of this polygon, meaning there are two vitamins that defines this vertex, that you're just on the boundary, and then you're continuing on the boundary of another vertex. Maybe easier to see in this spot. This would be the vertex. Now let's put the budget back into the game. Now we can finally compute what is my cheapest diet. So far, I just talked about what are diets that are healthy or not, but I put the budget aside. Let's increase my daily budget from 0.1 larger and larger. And right now, with a budget of $209.1, this is a line of all the diets that I'm getting exactly, that I'm paying exactly $209 on them, being on this line. So every point below this line costs less. What am I looking for? Do I have any diets that I can afford with this budget? Definitely yes. Every point in this intersection, it's a diet that I can afford in this daily budget and is healthy. Let's decrease the budget significantly. Remember, the line is parallel to itself. Now, with a budget of $40 per day, there is no diet that I can afford that is healthy. I'll have to give up at least one of the vitamins requirement. As I'm slowly increasing the budget, what am I looking for? When this line is moving parallel to itself, my budget line moving parallel to itself, I'm asking what is the first vertex of the feasible region that I hit? Because this is the cheapest diet that is both healthy and, this is the cheapest healthy diet. But move with this line. After you computed the feasible region, move the cost line, the budget line parallel to itself until you first hit a vertex. And this vertex is the cheapest healthy diet, the cheapest point in the feasible region. Okay? That would be the first idea of the linear programming. Okay. So linear programming, the geometry, general x and y. You have two half planes, a1x plus a2y, larger than b1, or another half planes, a2 plus x2. What happens with more types of foods with the same type of constraints, banana, oranges, avocados? Each constraint defines, one define is enough, defines now a half plane. In 2D, it will be a half plane. In 3D, it would be a half space, the boundary, that is what the point that I'm snagged, just a bare minimum of this vitamin, will be a plane, and we're talking about half plane. In 4 dimensions, put another food, in 4 dimensions, you're talking about hyperplanes, and you should have said hyper half spaces, but you still call them half spaces in 4 and so dimensions, just for not saying too long sentences. So each constraint defines a half space, some region in the D space, and the feasible region is the convex intersections of these half spaces, points that I can get. And talking about the case D equal to half planes, this equation y equal ax defines the line. Can write it in various ways. Why would I like to write the line in various ways? Because when you write the line in this way, y equals ax plus b, there are some lines that you cannot express. In particular, you cannot express vertical line in this way. if you write them in a closed form, then every line, including vertical, is fine. Okay. How is a feasible region looks like? One half plane, another half plane with their intersection, another half plane with their intersection. Now the intersection is a triangle. Okay. There are points that are in the intersection. Why intersection? Because you need to satisfy each one of the constraints. Okay. A bit more geometry. The solution to the linear programming, the solution would be the point that optimize my cost function, and my cost function needs to be linear. Otherwise, things fall apart. My cost function needs to be linear. Every point, every diet will be a solution to the linear programming. Is some point in the feasible region, which is extreme in the direction of the target function. Promo, in homework 2, I will ask you to look at a set of points and give me a good algorithm so that when I'll give you a cost function, you can find what is the best point. Anybody has any idea? Give you a set of points. And I ask you, think about them, pre-process them, meditate on them, get them into a data structure such that I will give you a cost function, c1x plus c2y, and ask which one of these points minimize this cost function. That is, when I'll put, will it be x1, y1? Will it be x3, y3? Which one of all these points in this whole set, when I'll put it here and here, I'll get the minimum value? Any ideas? It's discrete space. So it's discrete space. I gave you the points directly. Yes, sir?
You could like sweep the lines that define.
So I'm taking this line, c1x plus c2y equals some number, alpha. And then I'll start when alpha is minus infinity. That's absolutely correct. Alpha equals minus infinity. And then I'm changing alpha, changing my budget. And as my line keeps going from infinity, the first point that I hit, that's my solution. Great. Now, what is the data structure that helps you answering such queries fast? I'm making this question more complicated than it is. Preprocess these points so that I'll surprise you with C1 and C2, and you'll be able to find the best point quickly, the extreme point. If you want it, you think about it as the extreme point in the direction orthogonal to this line. I don't know. It's not a solution that I thought about. So I'll say that no out of arrogance, but possibly, but since I don't see it immediately, I'll declare it as no at the moment. The gentleman over there, I didn't hear him today. I can compute the angle and sort it by angle, and that will be linear time. And this is a fact that I told you. Now we are in relaxed time, so you have time to pre-process the data. But when I'll give you the queries, there are actually a lot of such queries, and for each one of them, you have to answer more quickly. Like hopefully linear time, I don't need the pre-processing.
Could you find the convex hull? So any of the points would be on the convex hull?
Absolutely correct. Compute the convex hull. compute the convex hull and think about it. As you are approaching, one of the points will be a vertex of the convex hull. Points that are buried here in the middle has no chance to be an extreme point. Right? Why? Because of the cat. Because if my cost function improved when I went all the way to an interior point, if I'll keep on going, I'll improve it furthermore. Right? So I only need to check vertices of the convex hull. And somebody is willing, without the details, to risk there next to say what would be the time to answer this query after computing the convex hull. The data structure, by the way, is just store them in an array. That's the only thing that you need. Store them in an array, but sorted in a counterclockwise order. And I didn't hear you? Log n time, it will be just binary search. Because for each point, you can decide, am I going clockwise, am I going counterclockwise? OK, so yeah, that will be, we'll figure out more details about it. So more geometry of the linear programming, the cost function C, C1 and C2. I can also think about it as a vector. You can think about it as an arrow that you can barely see, gravity, and it pushes your line all the way to here. So the point that you want might be either the first one or the last one. The last one, say, in this case, would be this vertex. So again, the cat, if I'm moving along this direction, I'm getting the best improvement of my cost. It's actually the direction of the steepest descent. The coefficient C1 and C2 that we saw before that. Theorem, when we described this polygon, we had infinitely many points on its boundary. If I want the best diet, do I have to check each and every point? No. There is only discrete many points that I need to check. So any bounded linear programming, bounded meaning that you cannot go to infinity. I could have presented diet as try to go to maximize or minimize your daily expenditure, and then you can go all the way to infinity. But if it's bounded, if the solution is not infinity, then any bounded linear programming that has a solution, some don't, but it has a solution which is also a vertex. Has an optimal point which is also a vertex. Why do I say A here and not V? Is because the solution might not be unique, depending on which direction I'm going to. Right? If I'll go in this direction, C is pointing to this way, then this vertex is good, this vertex is good, and every point in between is good. That's if my line is moving parallel to this edge. Nevertheless, it's enough to look for solutions that are vertices of this feasible region. Okay. And what's a proof of this really basic theorem, like really important theorem, that it's enough to look only for vertices, is to say, let's assume that I follow the gravity, follow the wind, I'm on an edge, and now, because of the cat issue, there is one direction of the edge at which, if I'll keep moving, I'll improve my cost, or at least there is one direction at which I will not decrease my cost. So I can keep following the edge until I'll hit a vertex. In 3 dimensions, it would be, let's say, that I hit a face, then I can move it until I hit an edge, and I can follow it until I hit a vertex, and so on. So it's true in any dimension. Convexity. Possibly, there is no solution at all. I could have set a few other constraints. Bananas has some things that are bad for you, I don't know. And you should not eat more than these many bananas. And here is my new setting, my 3 half planes. That is the intersection of the first two. Is this that has empty intersection with the third one. So it's possible that there is empty solution. There is possibility that it's unbounded solution, go to infinity, depending on the cost. And the solution might be, just repeating ourselves, might be non-existing or not unique, like in this case. In this case, if I'm looking for the lowermost point, let's say that my cost function points vertically down. I'm trying to minimize y, don't care about the x. You see two vertices that are equally good, and a lot of other points between these two vertices that are good. Simplex algorithm I'll tell you about it, and I'll tell you more how to use it. I'll tell you more about the simplex algorithm. Extremely important algorithm. Really, really important algorithm. Works extremely fast in any dimension, literally. You can throw on it thousands of constraints, tens of thousands of variables, still runs extremely fast. Like minutes of second for any realistic problem. And it works kind of like a greedy approach. Start in higher dimension. You start from one vertex. If it's not the optimum, then you can follow one of the faces until you get another vertex, and so on. Now, in 2 dimensions, you can afford to construct the feasible region directly. That's in 2 dimensions. You can even do it in 3 dimensions. It's less convenient. In higher dimension, it's hopeless. Why? Because if I take in d dimensions and I ask with n variables, d variables and constraints, how many vertices do I have in this polytope? That's a number, n to the power of d half, exponentially many. You cannot enumerate all of them in higher dimensions, so we'll have to find ways to just check a subset of the vertices. We are not going to enumerate all of them explicitly. Now, what's important here is why is convexity so important is because local optimality is global optimality. Everybody agrees? If I have a few constraints and I find a point that is locally optimum, which I can check by just checking these variables, that's also the global optimum. The problems with all the with the NP-hard problems is that when you look at the solution case is that they might have many, many minima. Each one is a local minima, but you need to find ways to move from one local minima to another. The fact that our cost function is linear, cat-wise, cat on the same direction, and all the constraints are linear, makes this problem way, way simpler and efficiently computed. And by the way, even if it's not linear, convex programming as a whole is way more efficient than non-convex optimization. Why? Because steepest descent will land you eventually to a local optimum, which is also the global optimum, and then you're done. OK, so far we didn't describe what is exactly computational geometry has to offer for the simplex problem, but I think that getting an overall idea about linear programming was good. Now, what I'm going to do, if you want me to, is after we'll discuss the computational geometry approach for linear programming in lower dimensions, I thought that to leave for a meeting or two the computational geometry part and show you what else we can do with linear programming in higher dimension and integer linear programming that is like one big tool that solves many, many problems and runs surprisingly really fast even for problems that are NP hard. So maybe 1 or 2 meetings, if you want, will not be pure computational geometry, but definitely algorithms with integer linear programming. So we can speak about it next meeting. Oh, and we still didn't decide about midterm parts, so please, for next meeting, have all your deadlines in front of you so we can vote and decide about one day.